So let's analyze an Atwoods machine, and that is simply a pulley, frictionless pulley, with a mass little m attached to one end of a string that goes over a pulley and the other end of which is attached to big M. And let's assume that big M is bigger than little m. And so in that case, we can draw a coordinate system here. Let's set y up. And we know that if big M is bigger than little m, that little m will be accelerating upwards like this, and big M will be accelerating downwards like that. So let's do a force diagram for each one of these two masses. And so for little m, we have a downward weight of mg, little m times g, and an upward weight force of T tension. And for big M, we have a downward force of mg, its weight, and the same tension that acts upward on little m also acts upward on big M, like this. And so, as we said earlier, little m is going to accelerate upwards, and big M is going to accelerate downwards. So we can write a Newton number 2 for each one of these. For little m, we can say that T minus mg is equal to little m times a. And for big M, we can say mg minus T, forgot to label that, is equal to big M times a. Alright, so we have two equations. So here they are. I'll put rectangles around them. Two equations, and we have two unknowns. We're going to assume that we know what little m and big M are, and we're going to assume that we know what g is. So let's write that down. So we know little m, big M, and g. For any particular problem, we would know what each one of these is. G is just going to be equal to 9.8 meters per second per second. And so the unknowns are T and A. Well, we have two equations and two unknowns, and so that's always what you want to look for. You want the number of unknowns to be equal to the number of equations. And so we can solve these. And so there's different ways of doing this. But if I call this equation 1 and this equation 2, you can see that if I add these two equations together, the t's are going to cancel. That's one way of doing it. I could also solve by substitution. But let me do it by simply adding equations 1 and 2 together, and here my strategy is to eliminate t. So if I do that, I get, on the left-hand side of the equal sign, I get mg, big mg minus little mg is equal to little ma plus big ma. So I can factor these out. That's going to be big M plus little m times a. And I can factor this out on this side. This is going to be equal to big M minus little m times g. And so you can see that if I divide through by big M plus little m, I get, switching the side that A is on, big M minus little m over big M plus little m times g. Okay, so that's my solution for A. That's the acceleration. Just to take a look at this for a second and and do some common sense type of reasoning. You should always do this anytime you find a solution to a physics problem. And so intuitively, I know that if little m and big M are the same, A should be equal to 0. Because if I do, there'll be equal weights on both sides of these. The tensions are going to be the same, and so neither mass will accelerate, and that is in fact what the formula predicts. So let's now use this to figure out what T is. And so I can use equation 1 to do that. I can rewrite equation 1 as T is equal to MA plus mg, just bringing the mg over to the other side, and that's going to be equal to little m times A plus g. But A is equal to that, and so that's equal to little m times big M minus little m over big M plus m times g plus g. Okay, so I'm going to rewrite g as big M plus little m over big M plus little m times g, so I get a common denominator there. And so what I get is I get m times g over big M plus little m, pulling the denominators out, and then I can just add the numerators together. And what I get is I get 2 times big M, like that. Okay, so let's write that in a somewhat nicer way. It's going to be 2 big M times little m over big M plus little m times g. That's my tension.